Our EECS project is a game of Pong using physical paddles. Each player controls the vertical movement of a paddle on either side of the screen. The ball bounces between the two paddles, and the objective is to hit the ball past the opponent's paddle. The first player to 5 points is the winner.
So we use OpenCV to track the paddles. So first things first is that we got to calibrate it. So we run a screen that's entirely blue with green in the corners. And so that generates images through this process in which we detect each of the squares in each of the corners. From that, we use it to map things to our game grid. From there, then we track yellow objects, and then we identify the center of the yellow object, and then we transform that to get our paddle position. This will track in real time, and then we can use that to play our game.
Alright, now I'm going to talk about some of the features we've got for controllers. So first we've got a button on here that allows you to serve the ball and also to transition between the states of the game. Then inside our controller, we've got, for the game, we've got a couple different power-ups. So we use the IMU to start power-ups. We have two different types. We've got, the first one is a spin power-up. So using the angular velocity given by the IMU, we can set the ball into a spin state where it does corkscrews across the screen. And then our second power-up is using the linear acceleration given by the accelerometer and correcting that based on the orientation of the paddle so that we have a horizontal acceleration and a vertical acceleration component, which allows us to control both the direction that the ball is hit at and also increase the speed when you thrust the paddle pretty vigorously. So then we're using XBees to communicate all the data from the paddles to our main Smartfusion board. We're using the API mode, and we've got a whole bunch of different message types that the Arduino is parsing and sending to the Smartfusion. And then finally, we've got a little vibration motor on here, and we use that for haptic feedback when the ball hits the paddle.
The heart of the game is our VGA display that creates all the visual images that we see on the screen. We do this by having a DAC. Basically, VGA is an analog circuit, so we feed in 2-bit colors per channel. So there's R, G, and B. We feed in 2 bits for red, 2 bits for blue, 2 bits for green. It converts it to analog voltages, and those get displayed as colors on the screen. The important part about our VGA implementation is that we follow a sprite protocol. So the idea behind it is everything on the screen can be dynamically placed. We store data of how the shape should look in a memory or in RAM on our FPGA. And we access that by using different types of registers to place positions of our elements and paint it based off of what's in memory. This allows us to put elements on the screen dynamically, change their positions, but without having to do complicated math or figure out exactly how to draw them in real time.
So we have 2 different sets of state logic, one in the hardware, one in the software. In the hardware, the state logic controls what we display on the screen. We have a pausing state, a gameplay state, and a winning state. And also a calibration state for the very beginning for this to calibrate the CV. In software, it controls the gameplay. So it'll be like player 1 or player 2 serve, check whoever wins and go into winning state. So an example of a state transition is currently we're in a winner state. As you can see, it's almost 25 points. Once one of the players presses the button on the paddle, it'll go back to the playing state, the serving state. And once I press the button again, the player will serve. Alright, so we play audio through the onboard DAC, and we feed it values by indexing through an array that we put in memory beforehand. So when it plays a sound, there is a timer interrupt that generates the audio. And so we have one sound for scoring, one for wall, and lastly one for winning.